In our study of the planes in surfaces in three-dimensional space, we want to make sure that we can identify a plane not only in its direction, which is specified by the normal vector shown here as ABC, and the point, or the vector rather, in the plane determined by 2 points, P and P0. So we would simply have to subtract those 2 points to get a vector in that direction, and then describe the plane with a normal vector. And as you can see, the normal vector can describe how the plane is tilting, what direction it is oriented, and other types of things, especially as we get into surfaces. So any point on that plane is going to be collinear with any other vector on the plane so that it does describe the point on each plane. So as we kind of look forward to complicating our life a little bit, that now we see two planes that have in the same orientation in this diagram, but that these vectors d, which is the right-hand side of my plane equation, d1 here and d2 on the kind of brownish one, show that each of these values, that once you determine the equation of a plane, each of the values kind of tells where it is in space. So one of the things, these two planes are parallel just to demonstrate the concept here, but one of the important tasks that we have to do is to find an equation for the line of intersection of two planes. And there's two planes given here, Q and R, and the important beginning point to make is that the normal vectors for Q is 1, 2, 1, and the normal vector for R is 2, 1, minus 1. And they're not multiples of each other, so that these are not parallel planes. The consequence of that is the planes must intersect at some line L. So as we do that and trying to find this equation for L, you need two things: a point on the line and a vector pointing in the direction of the line. In other words, if I'm going to create an equation of a line, I need to have a point x0, y0, z0, a point on that line, and then a vector pointing in the direction of the line, ABC, which that vector will be acted on by the value of the parameter t. So when we do that, what we do is let some value just find a surface. And one of the easiest ways, of course, to do is to let z equal 0. So the lines where they intersect on the xy plane are given by the solution to this set of two linear equations. So that, is that solving by substitution, we see that x is 3 and y is 1. And so that 3, 1, remember z was 0, is a point on the line. So we've found the first thing, a point on the line L. Okay. So the second thing is find a vector in the direction of L. And so that since this line lies in both planes, remember it's the line of intersection of the plane Q and the plane R, that it's orthogonal to the normal vectors of each one of those. Okay, so that if I go and create the cross product of those two planes, that's a vector parallel to the line I'm looking for. So I can do the computation, and we find out that this vector minus 3, 3, minus 3 is a vector in the direction L. And then all we have to do is add that point in the beginning. That's where the point we found by letting z equals 0, and the vector that we found by creating the cross product of the normal planes into a line. One of the most difficult things is to keep track of whether you're talking about a plane and what the equation of a plane is, and that is given by these two planes here in the beginning. That's an equation of a plane, and that's an equation of a plane. As we saw in the previous figure, that the value 7 here would be a parallel to if the value was 5. It's a plane just displaced in space a little bit. So if we want to check this answer, we just let the parameter t equals 1, substitute that into my value here and get 0, 4, minus 3, and then check by putting it back into the equations of Q and R and finding out that the plane value is 5 and 7 as they were in the beginning. Okay, so that's starting to work with the idea of planes, and that example was finding a line at the intersection of two planes. A slightly more complicated subject is the subject of cylinders, and it has a different meaning than what you mean when we just use it in a regular language. So here C is just a line in space, and that what we do is create one line orthogonal to it and then lines parallel to that, and that creates this surface, so almost a curtain type of surface for this one. And that's what a cylinder means, is that you have a line, you create perpendicular lines, and then allow that perpendicular line to propagate along the given one, given curve so that you can create a cylinder, and that's the technical term. In a similar way here, we have two versions where this curve is y equals x squared, kind of what you're used to seeing, and if we create a cylinder, we of course get an upright type of folded figure here. And the only difference here now is that if I'm going to orient this in the y equals z squared plane, that I would just have a differently oriented cylinder, but the same type of surface. If we continue with looking more and more into figures, one of the things that we're going to have to do is to sketch a cylinder in order to kind of figure out the differences as we work with our quadric surfaces. So that the first basic idea is to create a basic trace. And remember, this one here is the easiest one is when z equals 0. So this is the trace of the curve on the xy axis. So then to create this cylinder, we just translate that up and create another similar curve up in space a little bit for another value of z, and then draw parallel lines and then create the cylinder as we kind of can continue to fill in around this space, right? So that you can see the traces in the different values of z, and that we just continue to kind of build that surface as we fill in each value. This one's a little different. It's a curtain more, and so the same idea. We draw a second trace slightly offset from the first one, and then draw parallel lines and fill those lines in until you get a surface. Okay? So that this is helpful to visualize these complicated figures. So that as we start to work with these, what we're going to do is have these three-dimensional figures, and this is an ellipsoid. You can see the equation here, x squared plus y squared plus z squared, and that to create these traces, all we'll do is take a given value, and that's exactly what it means here, is I choose a given value of x0, and that in this case is 0, and then I can change that here, and you'll see that all I'm doing is just going along that surface and creating traces as I do. Okay, so we can do that with each value of the parameter. Let me turn that a little bit. So this is the parameter y, and then also with z. Okay, so that's kind of the more familiar one that you're thinking you're going up and down the z-axis, and what does that figure look like? So that let's do another example of a figure here, and this is a bowl type of elliptic paraboloid, and that just the value of z is given as kind of a elliptic for the non-equal denominators, so it's not a circle, and that we can continue to create these traces as we go back and forth along an axis at given values of each individual component of the curve. Okay, so that the traces are very useful because they allow you to visualize a three-dimensional figure in 2 dimensions. And so as we kind of work through these figures, we will start, start to look at if we think about, well, if I give a given figure, what would that look like at a given value of z? And in this particular example, the value of z is 2. And so we try to kind of visualize what would happen if we took that figure and created these contour lines. And this figure shows that, so that as I move back and forth with the value of z, you can see the plane on the right moving up and down, is that these intersection lines, this thick line here almost going through the origin, is the one shown here, and then here's another one, and here's the other one, with these uneven contour lines in between them. So I can tell that going from this point here to this point here is going to be very steep when these contour lines are packed together, kind of shallow as it goes along its bottom point there, and then rather steep as it comes into this other one. In other words, as I go along this figure, I'm going steep through this section right here, kind of shallow or not a lot of changes, or as much change really, through there, and then steep as I come back into this second line here going near the origin. Right, so as you kind of get more familiar with learning these contour plots, you can get a good idea of what a figure looks like by looking through what the contour plot looks like. And again, here's an example of the value of p changing as it encounters the surface. And if we look at the contour lines for this one, that now we start to look and see, well, that's quite a bit different as I go through there. Right, you can see the thick line is the intersection, and the value of the plane, how I can see and look at as that goes back and forth as each parameter changes. Right? So these are very powerful and useful figures in order to determine what a three-dimensional figure looks like in 2 dimensions. And this is a electron charge diagram, and so that you can see that the charge is greatest here in these little kind of smokestack figures, and that this value phi is a parameter that describes that charge. So that as I'm kind of moving out, and I can see myself moving into the cylinders and back and forth, and it gives you a way of determining how that figure can work in space.